Welcome to Translating Proteomics, where we explore the science of proteomics and its growing impact on basic biological research, drug development, and more. In this episode, we cover AI in biomedicine and specifically discuss why we're ready to apply AI to problems in biomedicine, how we can better leverage AI in biomedicine and overcome current limitations, and potential dangers of AI in biomedicine. And now your hosts, Parag, Malik, and Andreas Humer of Nautilus Biotechnology.
Welcome back, everyone. Today we're talking about a topic of incredible importance, both in society and in biology, AI. Andreas, AI, it's everywhere.
I know, it's everywhere.
Tell me, what are you feeling about AI?
So I think if we talk about machine learning and AI, the first thing we need to acknowledge is really the progress that has been made with AlphaFold. I think that to me was the first really compelling use case of application of artificial intelligence in our area, area of biology. The fact that we can take a random string of amino acids and literally fold them up to the point where it is coming pretty close to what you might get if you look at this with a traditional tool like NMR or X-ray, I think is very impressive. I think it's the very beginning of it, and I think it's super exciting to be actually in the field of proteomics today and living through this what I think is a revolutionary step.
Yeah, so it's interesting. I think AlphaFold, deservedly so, got a tremendous amount of attention focused on AI in biology. But on the other hand, AlphaFold was built upon innovations that happened over decades, ways to represent protein structures as contact maps, ways to take a protein structure and understand where the variation is, ways to that encoding step took years to perfect, and then the computation to do those predictions beyond that and to get in and out. While it burst onto the scene, it was decades of work to get to that point.
And I think just to second that, this progress of AlphaFold was not only built on previous work, but it had to, it took advantage of these enormous databases we have.
Yes.
And I think these databases were well curated, they're standardized, so it was relatively easy for machine learning models to sort of utilize that resource.
So when we think about non-protein structure data, when we think about proteomics data, transcriptomics data, what are the challenges that you see to applying that same sort of machinery in those domains?
Yeah, I'm afraid we can't fall back on the resources we had for AlphaFold, because we don't have simply the collection of well-curated data sets, in the context of a biological mechanism, for example.
So, but we have things like PRIDE, like the Proteome Exchange, which contain thousands of proteomics data sets. Why is that not good enough?
Well, I think you could probably learn something about compositional studies, of compositional changes in maybe different cell types. But if you really want to observe biology over space and time, again, you would have to have different collections of data sets.
So let's maybe take a step back. What's different today than 5 years ago, 10 years ago, 20 years ago that, from your perspective, has enabled AI?
I think I would bring that question back to you as the computational scientist.
Fair point.
And say, why now? And why would it be now the right time to actually invest more in that area?
Yeah, so to my mind, there are really three elements to that. The first you mentioned already, which was access to well-curated, labeled data and having a sufficient scale of data that was learnable over. Number two was just compute power. The acceleration we've had in GPU compute over the last 10 years has been astonishing. And all of these models rely upon these kinds of infrastructure. I'll also just point out that beyond the compute power, there's also storage. These models are large, and so the infrastructure for storing data is tremendous. And then I think those combinations, there have also been some tremendous algorithmic advances in how we represent foundation models, large language models, et cetera, that these are very new approaches.
But if you talk about curated data sets, right, you could immediately say, well, why don't you just learn how to read all the literature that is out there on, biological systems and then tell us how they work, right?
So I've done that. So my lab actually was working on that problem of reading biological literature, and it is incredible. It is an incredibly challenging problem.
Why?
So there are a couple of reasons. One is that our terminology in biology is terrible.
Yeah.
So, for instance, if I were to, our publications are filled with acronyms. So MBC. This could be a maltose binding channel. This could be metastatic breast cancer. A machine learning tool. So there's a step called grounding, which is about taking a term and relating it to a very specific ontology. That step in reading biological literature is quite complicated. Also, the context of reading those papers and how there's information that maybe reading one sentence is fine, but if I need to read a whole paragraph or I need to read a series of paragraphs in order to interpret one sentence, that distance makes learning extremely challenging.
So do you think we're ever going to get to a point where when I read a scientific paper, right, I typically look at the results section first, convince myself that the data somehow makes sense, and then, read the text that, is the result section, and then ultimately, digest the discussion. Do you think we'll ever be at the point where, algorithm can do type?
So I think this is a place where there's an opportunity for interaction, so human-computer interaction, so that maybe as we're writing the paper, there's a plugin in Word, so that when we type a protein name, it pops up something that's like, oh, are you talking about this protein? And it identifies it in UniProt. And so that our papers are no longer just these static one-dimensional things, but they're already linked to a broader collection of knowledge. So then the extraction problem is so much simpler because as you're writing it, you're elaborating your hypotheses, you're grounding it to the terms that are relevant to your paper. So the machine learning tools don't have to do as much of a lift in order to interpret them.
Yeah, and I think that's similar about how I think, AI should, at least that I view it. I think more of an assistant rather than a replacement for what I do.
Yes.
And I think if we perceive machine learning tools as tools that ultimately can hack through a lot more data than we can, may not be able to interpret it, but they can definitely digest more data and more dimensionals that we as humans can, then I think we're going to probably have a great partnership between computers and humans where, we have computer-assisted scientific explanations.
Yes.
Where we need graphics, we have computers training the graphics or the models.
Yes.
Where we need, details that we otherwise cannot unravel. Computers will help us to find those patterns, right, that we cannot find in highly dimensional data. So I think, while AlphaFold may have been, really transformative and will be transformative, I think AI has probably a very important role moving forward for us in the field of life sciences when we have to digest huge amounts of data, incredibly complex patterns, and patterns that are probably not consistent enough for us as humans to recognize. As we talk about artificial intelligence, there's certainly also limitations. What do you think are the limitations?
So I think when we think particularly about the application of AI in life sciences, one of the simple ones is data size. We think that we have a lot of data in life sciences, but if we compare to some of the training sets that some of the large language models, for instance, use, they were trained over the entirety of Wikipedia or the entirety of the internet. They potentially have trillions of parameters and are resident in memory with petabytes of storage. In life sciences and healthcare, we have diseases, for instance, that may only afflict 100 or 1,000 or 10,000 people a year. So we will never reach the point of having trillions of examples.
So would you think the concept of what's called a digital twin is emerging that helps us cover those gaps?
So absolutely. So one can get around these limitations in data size. And really, there are two ways that people have been going about it. One is by generating synthetic data that, and they can add noise to it and make it increasingly realistic. The other is by building models that are less sensitive to data volume. So we talk about large language models. There's a competing class of small language models that are being built specifically to address this challenge of low data environments, which we often are in life sciences. Some of the other challenges that we have are time. As we discuss in another episode, time is really important in biology. The current set of AI tools are not great at learning temporal trends. They're not great at learning from temporal data. They also anticipate that data is uniformly sampled. And if you think about a patient going into the doctor's office, it is very unlikely that they're going to show up on an exactly regularly scheduled cadence. And so these sort of small technical hurdles have currently been a challenge. I don't think they're unsolvable, but they're practical challenges. And to me, the really most critical limitation that AI tools have today is meaningfulness and explainability.
Yeah. I mean, it's often quoted that we cannot explain how the large language models work, really, and it's demonstrated that they not necessarily understand what they're talking about, right? But I think, as you said, the excitement for me is that for places or data gaps that we might have, you just mentioned one, we may have one or two lapses of temporal data points that these artificial and intelligence approaches allow us to fill those gaps, right? Because they have learned over massive amounts of data that there's only a limited space these data points can be living in or can be filled with. And so I think that's where probably some of the sweet spots are.
So I think that's true. One thing that we have to be aware of, though, is that oftentimes in biology, the things that we're interested in are the extremely rare events, the things that are on the extreme tail of the distribution that don't happen very often. That's when a disease happens. That's when, and so definitionally, you have a small amount of data for a given thing. You have even smaller data when it comes to the extreme rare behaviors. And so finding ways to sample those rare things and characterize them is a huge need that we have.
On the other hand, I would challenge you a little bit on that, because I think we talk about the temporal aspects of biology, and I think to measure discontinuity,
yes,
where you see some kind of jump or some kind of change of pattern, probably doesn't require huge amounts of data set. It's simply because the entire pattern changes.
Yeah,
and those may be sufficiently recognizable, even for humans or definitely for machines, to be able to sort of capture those moments, I guess.
That's right. So if you have large effect sizes, then you need a smaller amount of data to look at it. And it's only when you get these compounds of very small effects leading to some very large consequence that things get very difficult.
Yeah, absolutely.
Changing gears, when we think about where AI is going to have the most impact, and let's talk specifically about proteins. We've talked about AlphaFold, but where else do you see AI having an impact on the study of proteins?
I think immediately, obviously, the tools that we have today that measure proteins are going to be much better. And examples are out there with interpretation of, let's say, mass spectrometer data. Certainly all the other protein measurements we'll be doing in the future will be aided and embellished or make better by artificial intelligence. I think more of what I already mentioned is that we can't, predict certain things, or we cannot measure certain things like the structure or every single protein form, or that we actually fill those gaps, through, what we could call now linear extensions, right, or regressions. And then we're going to be much smarter about these regressions and not using just the most simplistic model, but maybe more sophisticated model that are informed about, how these biological systems or how proteins, would be, filling that gap. So, for example, it bothers me a lot that when we look at data today in biological systems, we don't do a mass balance or energy balance. We just assume these are all open systems with unlimited energy and mass.
There are constraints.
There's constraints. And so maybe computers can help us and say, by the way, that observation you just made would also assume that 500 other proteins have to change either, because they're modified or degraded.
Yes.
And if we had a computer model or an AI that would tell us, hey, wait a moment, the observation you're making is only valid if you actually can confirm there's something else big happening there, then I think.
So you interestingly you accidentally conflated two things, which I think is actually at the cusp, the bleeding edge of AI. So what you mentioned in the same sentence were models and simulations and AI. And typically those have been completely distinct universes. And it's actually been really hard to get our existing knowledge, our existing models, concepts like gravity, to teach an AI, hey, we have this prior knowledge. But in biology, we have a ton of prior knowledge. We have an understanding of signaling networks. We have understandings of many core principles. And so one of the huge opportunities that we have for bringing down the amount of data that's required is actually getting AIs to be smart enough to understand models of how the universe works. And so that we actually will be able to combine those two worlds of simulation and physics-based modeling with the worlds of AI. Today, they're pretty separate, but there's a huge effort to bring them together.
Wow. Yeah, I wasn't aware of that. But clearly, all of this indicates that we just need more data, and more data that are reproducible, that are high in quality.
Yes.
And that they're highly annotated. And I think we go in this directions. I mean, the efforts around the cell atlas, the efforts around, particularly in proteins, around the protein atlas, sort of the first real big steps towards having repositories where we can, deploy AI on.
So for me, one of the things that I'm most excited about is we've been talking about proteins, and we tend to talk about proteins as changes in abundance, changes in movement. And then we have this other universe of protein structure. They clearly connect to each other. How we modify a protein, the percent of what's modified has a change on the structure, which has a change on the behavior. And so ways to take advantage of these architectures to say, oh, okay, I observed this proteoform. And so, hey, let me take that observation of this proteoform and make a structural prediction about, hey, what's happening? Are you more likely to interact with this person or this protein or that protein? To me, that's really exciting about being able to leverage interactions between modalities and the AI really unlocking that.
What's holding us back? Because I think at the very same vision that you have is if we can fold proteins already in a computer, even if they're imperfect, but I think we could get a pretty good idea, is this particular active form of protein we just measured going to have any impact? And how big is the impact? I think that should be a regular tool set that, proteomics users are going to be using in the future.
Yeah, I think it's just so new that the community hasn't had a chance to plug those together, and that's a tremendous opportunity for us.
I totally agree. Yes. AI, obviously a lot of people are excited about it, but also people are getting aware of some of the drawbacks of applying these technologies. Do you see any danger that we might be applying these tools and, getting misguided maybe?
So I think there are two very disparate pieces to this. One is intentional bad actors, and the other is unintentional bad consequences. And I think they're very, very different. But one can imagine that intentional bad actors might use these tools to fake data.
Yeah.
That would be really hard to know that it's fake. You might find that people are using these tools to, on a far bad actor side, there might be, hey, it's so much easier for me to design variants of different bacterial species. Can I develop a new superbug? I think there are potential bad actor ways that these could be used, both for misleading science. You can imagine publishing a series of papers saying, oh, hey, this is the coolest, best new thing, and distracting the scientific community for years, or drowning in a public-facing way, creating billions of blog posts about, hey, some scientist said this, and this is either your new miracle cure or this is going to kill you, and drowning out legitimate information from fraudulent information. So I think those are possibilities. I'm hopeful that we'll find ways to combat them. The other side is also interesting, the inadvertent risks of AI. So one that came up recently was in the space of radiology. So huge interest in using AI tools to predict or classify images and say, do I see cardiomegaly? Do I see cancer, et cetera? And if you just think about your own experiences with Google Maps and your awareness of your geography around where you live, would you say that your understanding of your geography is better or worse now that you have Google Maps on your phone at all times?
Yes, I try to avoid the situation you're describing by going outside once in a while and exploring my environment, yes. But you're right. I mean, you could be misled thinking you know where you are, but in fact you don't, right? Particularly if you think about emergency, right?
Or even just simply your spatial awareness. You don't need to be aware of the streets near you because Google Maps will tell you how to get there.
Yeah.
And so a similar phenomenon there was a study done looking at radiologist interpretation and accuracy of interpretation and atrophy of that as a function of using these automated AI tools. So there is an accidental risk that we are making our diagnosticians maybe not as aware because they have these tools as a crutch. Now, the flip side of that is that maybe we're making them more effective because we have these tools in their pocket. But I think we need both of those to work together in order to make sure that we are taking advantage of the tools, but we're not moving ourselves into a world where we're so dependent upon them that we're making mistakes.
Yeah. So listening to this conversation we're having, I think my conclusion or takeaway is that, we're definitely, going to benefit massively from these new computational tools. Of course, if we have to pay attention that we don't overuse them or don't get blindsided by them. But ultimately, every data point we might be generating in the future might be so much more, worth because in addition to, having artificial intelligence support us in interpreting the data sets, we're also building ultimately a knowledge base.
That's right.
That we can utilize in the future.
That's right. I think there's tremendous leverage. I think there's a world where every experiment that we do across all of life sciences contributes to this broader knowledge that we all are able to leverage.
Yeah. Exciting.
It's really exciting. Thanks so much for joining us on this adventure through AI. Look forward to seeing you next time.
We hope you enjoyed the Translating Proteomics podcast, brought to you by Nautilus Biotechnology. To contact us or for further information, please email translatingproteomics@nautilus.bio or scan the QR code on your screen.